Thank you a lot to the speakers that had to wake up very early this morning. We appreciate. So the first speaker will be Federica Maria Surace. She has been studying in Pisa University, in Scuola Normale Superiore, eventually, when she moved to Suiza, where she got her PhD. And then now she's in Caltech. And she works on out of equilibrium dynamics of many body systems and quantum simulations. Today, so she will talk about quantum simulation of lattice gauge theories with Rydberg atoms. This lattice gauge theory is the field I come from, so I'm very happy to go back a bit there. And so please, again, I will tell you after maybe 20 minutes that you have 5 more minutes, and then we'll have questions after 25 minutes. Go ahead. You can share your screen, I guess.
Yes. So first of all, thank you very much for the invitation. And okay, so should see my screen now. And so yeah, in this talk I will talk about quantum simulation or lattice gauge theories with Rydberg atom. And so to introduce the topic of quantum simulation, I want to start with this picture. So here you can see this is a picture from an experiment, and in this experiment, like these dots are single atoms, and here they showed how they can really assemble these atoms in any geometry in 3 dimensions. So I think this picture shows very well how today this kind of tabletop experiments can control quantum system to a very high level. And here each atom has its own energy levels. It's a quantum object. And so from this came the idea that this kind of controllable quantum systems could be used to study other quantum systems that are more difficult to understand. And this is the basic idea of quantum simulation. So we can study problems of condensed matter physics, quantum chemistry, or high energy physics using this kind of quantum systems as some simulators instead of using numerical classical simulations. And so in this talk, I will focus on the applications to high energy physics. So why are quantum simulators useful? Like, how can we use them? So the idea is that, for example, in high energy physics, what you probably want to do is to do the following. You start with building up a model. So you have your theory, you want to compute what are the consequences given this model, and then you want to compare this prediction with experimental results. And the step where quantum simulators could be used is this one, because here you probably need I don't know, supercomputers to compute these predictions, and so this can be a very important computational challenge. If you think, for example, of quantum chromodynamics, here, I mean, you know the Lagrangian, but if you want to find what are the masses of hadrons and many other physical properties, you need to use, for example, Monte Carlo simulation in lattice QCD. And so, yeah, these methods have been very successful in the last 50 years, but there are some cases where you cannot use Monte Carlo simulations. And one case is when you have a non-zero chemical potential because you have a sign problem. Another very important issue is real-time dynamics, because with Monte Carlo simulation you can study equilibrium property, but you cannot study real-time dynamics. So, and if you think of, for example, collision experiments, this is a very important aspect. And then also in other cases like nuclear matter at high density, pressure, or temperature, there's many cases where you cannot rely on Monte Carlo simulations. And so the idea is that these intrinsic limitations of classical simulation do not affect, in principle, quantum simulations. And so, for example, entangled state of matter, real-time non-equilibrium dynamics, these are all things that are naturally encoded in quantum simulators. And for this reason, now there is the hope that one day we can use these quantum simulators to learn something new. And some of the long-term goals would be to obtain some improved prediction from chromodynamics background in scattering experiments, or for example, study the equation of state for nuclear matter, quark gluon plasma, or the early universe, or perhaps study beyond stardom model physics. And for all these problems, what we need to do is we need to design quantum simulations of gauge theories, because gauge theories are the fundamental theories that describe, of the standard model. And so what do we mean by a gauge theory? So there are typically two ways one can think of gauge fields. So one case is the case of static gauge fields. So here, if you have, for example, some particle that hops on a two-dimensional lattice, if the hopping is complex, it can happen that when your particle hops around the plaquette, it will acquire a phase. And if this happens, then you can think of this phase as the effect of a magnetic flux that threads the plaquette. So this this is like a gauge field. This magnetic field is a gauge field, but it's a classical gauge field. It is static, so it's something that you're controlling externally. So here, for example, is a picture from an experiment where they had this type of gauge field. This was done in Florence at Lens, and what what we're actually interested in is instead the case of dynamical gauge fields. So here, these gauge fields are instead additional degrees of freedom that reside on the links of the lattice. So these blue objects here, and so you should really think of them as quantum degrees of freedom. And this kind of theories are found in many different contexts. For example, in condensed matter, when you study frustrated magnets, in quantum computing, because the toric code is a lattice gauge theory, or as I said before, in high energy physics, of course. But despite the fact that these are so ubiquitous in physics, it is actually very difficult to engineer them and to have them in a controlled system. And the reason is that you need to be able to realize some complex many-body interactions, like this four-body term, that's a plaquette term. And at the same time, you want to preserve some local symmetry, which is the gauge symmetry. So, okay, so what has been done so far? So the first experimental demonstration, this was done in 2016. It was done using trapped ions. So here they had 4 ions of 4 qubits. And this was a simulation of a 1+1 dimensional quantum electrodynamics. And what they showed here was that you can, for example, study the real-time evolution of the bare vacuum and see how particles are produced out of the bare vacuum. And okay, so this was the first experimental demonstration. Then in the last years, there's been a lot of progress using so-called hybrid quantum classical algorithms. And here, the idea is that you want, for example, to find the ground state of your lattice gauge theory. Used for the abelian and for non-abelian lattice gauge theories. So this was done also in a digital way, so with using gates. But what I'm going to focus in this talk is instead the case of analog quantum simulation. So here you're not using gates, you're using an Hamiltonian that you can map to the model that you want to study. And so I will discuss this experiment where they simulated a 1+1 dimensional quantum electrodynamics. And the analog quantum simulation is, of course, less flexible than digital quantum simulation, but the advantage is that at the moment it can reach much larger system sizes. So here, this experiment was done with 51 atoms. And yeah, this is the reference for what I'm going to discuss, and then I will also discuss some follow-ups from this work. Okay, so this is the outline then for the rest of the talk. I will first describe the experimental setup based on Rydberg atoms. Then I will describe the lattice gauge theory that we want to study. I will show that there is a mapping between these two. And then I will describe some of the phenomena that one can study with these quantum simulators, for example, confinement, scattering processes, string breaking, false vacuum decay. All right, so this is the experimental setup. So here in this experiment, this was done by Luking's group in Harvard. They had a chain of atoms, so each atom was in a fixed position here, and each atom can be in one of the two internal states, either the ground state or an excited state. So this is the Rydberg state, the Rydberg excitation. And the Hamiltonian describing this system is the following. So there is this term, this is given by a laser with Rabi frequency omega, and this couples the ground state and the Rydberg state. So this is what sigma x is. And this term here is the energy of a Rydberg excitation. So this is the tuning delta, and this nj is the number of excitation, can be 0, 1. And this last term here is the interactions between Rydberg excitations. And so these interactions decay as a power laws, 1/r⁶. And in this experiment, they were working in a regime where nearest neighbor interactions were very strong, but you can neglect next to nearest neighbor interaction and longer range ones. And so what we're going to do, we're going to assume that nearest neighbor interactions are so strong that you cannot excite two neighboring atoms at the same time. Okay, so we have this constraint on our Hilbert space, and we will neglect all the interactions that have longer range. So this will be our Hamiltonian, and this is the constraint on the Hilbert space. And so this model has been studied in both first phase diagram and its non-equilibrium dynamics, so there's many interesting properties. But what I want to discuss here with you is its interpretation as a gauge theory. Okay, so to define what the gauge theory that we're going to study, we need these ingredients. Well, we need, first of all, matter. So this is, in our case, this would be fermions, spinless fermions with this I and J are lattice indices, and these fermions satisfy usual anti-commutation relations. And we want them to represent both our positrons and electrons. So what we do, we use the so-called staggered fermions formulation, where on even sides we say that a fermion represents a positron, while on odd sides a hole represents an electron. And this is shown to give the correct continuum limit. Then we need some gauge fields. So as I said, this will be on the links of the lattice, and we define two operators. We define E, the electric field, and we define U, that's called a parallel transporter. And this is the commutation relation. And so in this case, it is convenient to represent these operators as spin operators. So this E will be the SZ operator, and this U will be the S plus operator. So this is satisfied. And in particular, we will focus on the case where this is spin 1/2. And so we have two, so the electric field has two eigenstates. I will pictorially represent with these arrows going to the right or to the left. And okay, so this is our gauge field. And then the last thing is, of course, a gauge symmetry, so a local symmetry. And these GJs are the generators of the local symmetry. And here, this term here is the electric field going out of side J. This is the electric field coming into side J. and this is the charge. So this is defined such that this is +1 for the positron, -1 for the electrons, and 0 in the other case. Okay, so here we have the electric flux minus the charge. And so what we're going to assume is we will only consider states that satisfy this constraint. So where this Gj is applied to the state is equal to 0 for every j. And you immediately see that this means that we are enforcing Gauss law on our state. So the electric flux has to be equal to the charge. And yeah, and the last thing, of course, is this has to commute with the Hamiltonian, because this is a symmetry. So the Hamiltonian is the one that I'm writing here. So we have a first term, which is a matter-field interaction. So here you can think of this as hopping of fermions mediated by the gauge field in between, in the link between J and J+1. Then there is a mass term, so this gives mass m to electrons and positron. And then there is the electrostatic term. So this is the usual, the integral of electric field square. It's just that we include a constant here to allow for a possible static background field. So, well, you can check that this commutes with the generators. And so to summarize what I said so far, I introduced a U1 lattice gauge theory constrained by Gauss law, which means that we have positive flux coming from positrons, negative flux for electrons, and no flux in all the other cases. And we don't allow for states that violate this rule. And on the other side, we had this Rydberg atom experiment where we had the Rydberg blockade. So Rydberg blockade means that you cannot have two excitations that sit next to each other. So we have two constrained systems. And what I'm going to show now is that there is an exact mapping of states and of Hamiltonians between the two. So this means that we can use this model as a quantum simulator for this lattice gauge theory. Okay, so the mapping is the following. Let's start from the states. So if you consider, for example, these two states, I will call these states the charge density waves. So these are states where you have a Rydberg excitations on every even side or on every odd side. So these two states, we will map them to states with uniform electric field, either negative in this case or positive in this case. And then every time we have a domain wall between these two states, this will correspond to a charge. So here we have a domain wall between a positive electric field state and a negative electric field state, and this will be an electron. And here instead, we have one between the negative and the positive electric field, and so this will be a positron. And notice that because of Rydberg blockade, this domain wall can only sit on odd sides in this case here, so between the plus and minus, and on even sides for this case. So it means that that our electron will be only on odd sides and the positrons only on even sides, just as we wanted them to be. Okay, so here we have a mapping between the states in our computational basis. The other thing that I'm not going to show it actually, but I will just tell you that if you apply this to, if you see what this mapping of states means for the Hamiltonian, you will see that this will correspond to mapping these terms. So you will map the matter field interaction on this term, the Rabi frequency term of the Rydberg Hamiltonian. Then you map the mass term to this homogeneous, like the tuning here. And then the electrostatic term is mapped again to a detuning, but this time this is staggered, so this is not homogeneous. And okay, so this shows that we have a mapping also at the level of Hamiltonian, and so this means that we can interpret the dynamics of a Rydberg atom array as the dynamics of a U1 lattice gauge theory. And so this is what was done in the experiment. Here they had, so this axis here is time, and here they have the occupation of all the different Rydberg states. And here this one is one of the parameters of the Hamiltonian that they're tuning in time. So what they do is they prepare essentially the ground state of the Hamiltonian for a very negative value of delta here. And in this case, the Hamiltonian is ferromagnetic. So in this phase, the ground state breaks Z2 symmetry and chooses to be in one of the two charge density wave states. And then this delta...
20 minutes are gone.
Okay, thank you. And then here, delta is suddenly quenched to value 0. And the way we can interpret this is that we start from a situation where we have two minima and we are in one of the two symmetry breaking ground states, and then we change our potential to the paramagnetic phase, and then what we will see in the dynamics is the following. We will see oscillations between these two values of in this case of the electric field. And so here what they see is indeed that they have oscillations between the two different charge density waves. So to summarize, a Rydberg atom array can be used as a quantum simulator for a 1+1 dimensional quantum electrodynamics. And then one question we can ask is, what type of phenomena can we simulate with it? So one of the things that we can study is confinement. So confinement is QCD, is the phenomenon that traps quark into composite particles. So here you can see two quarks and the gauge field in between. So we can try to do the same. We can take two particles, positron and an electron, and and with a string of electric field in between, and we can see what happens, and we let this evolve in time. And what you will see is that if you're in the deconfined phase, these particles are free to move. And instead, if you're in the confined phase, then the particles cannot move. They will be trapped into composite particles, and they form what are called mesons. So these are so what we see here is actually how these particles are trapped into mesons. And one interesting thing that we can do with mesons is we can think of preparing two of them, giving some momentum to the two of them, and to make them collide. And then we can ask the questions, okay, what are the possible final states? What are their scattering amplitudes? So this is something that we studied in this work. I'm not going to discuss this. And but the interesting thing is that in the collision, you can have generation of entanglement, you can have creation of new particles. So there's a lot of interesting physics here. And then another thing we can study is string breaking. So what we mean by it is this. So if we prepare a string, so like two particles at a distance L, if this L is very large, then the energy of the string that's proportional to L can be larger than twice the particle mass. So if this happens, then this string is unstable because it can break in two smaller strings like this. So we can study this problem, and also the problem of false vacuum decay, where this string is infinitely long. So to summarize, quantum simulators of lattice gauge theories can help to study a rich variety of phenomena of high-energy physics. A U1 lattice gauge theory is naturally realized in Rydberg atom arrays, and present-day quantum simulators can be used to study confinement, scattering processes, string breaking, and false vacuum decay. So let me thank some of the people who were involved in all these projects, and I thank you all for your attention.
Thank you so much. I succeeded to enter again. Also, very perfect timing. Very nice seminar. Thank you so much. So there are questions. If you have a question, just come out. I mean, even if you don't raise your hand. I have a question to start with. I mean, somehow quantum prevalence, or in any case, how much I can do with this method now, how much you will be able to do in the future. So you never really talked about size of systems, and also somehow which size you need in order to really understand infinite volume physics, or I mean something like that. Mm-hmm. So which are your comments about that? I mean, what can you do now? What will you be able to do in the future?
Yeah, so here, for example, so in this experiment, they had 51 atoms, which is, well, this is of course far from infinite volume limit, but still this is much larger than what you can study, for example, with exact diagonalization of like exact methods. So this means that we're already at a stage where, you know, we classical simulations cannot do better than this. The thing is, still, this works for a limited time because you have a certain coherence time in your experiment, and you have other limitations. You have other defects, other problems, and so what concerns system sizes now, there were other experiments, for example, in 2D when they could reach, I think, about 100 atoms, so more than 100 atoms, and so the question is like, what is the size that we need to see something interesting? And this is really a big question, in the sense that if it's enough for us to see, for example, qualitatively, some of these features, for example, I don't know, a confinement, or I mean, we can have proof of principle of all these effects, but before, like, okay, we're very far from simulating QCD. This is something.
Yeah, right. If you want to compute CP, I mean, yeah. But
yes,
still,
but still, at least for these simpler models, we can already have very good results already with these system sizes, I think.
Okay, thank you so much. Any more questions? Anybody? Okay, listen, if not, really, I thank you so much. I will clap. Now, I don't know if someone else will clap, but I mean, thank you.
Thank you.